Hey, what's happening? Lecture 65. We'll do some more general review. Okay, again, just random and putting things together and trying to remember the stuff we've covered. Okay, so let's start. Significant figures, SF, San Francisco's. Okay, here we go. 10001, right? Four San Francisco's, four significant figures. I have a decimal place there. What if I took the decimal place away? It's still four significant figures, right? Doesn't affect anything. Let's look at this. There's a decimal place. Trailing zeros are significant when you have a decimal place, and all the zeros to the left of the first non-zero digit are not significant. So this simply has two significant figures, okay? Trailing zero. Here we have two zero 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 zero, no decimal, so trailing zeros are not significant. That has one significant figure. If there was a decimal place there or anywhere, all the zeros would be significant. Even if there was a decimal place in front of the two, then everything, this would have five significant figures, okay? All right, zero, not significant because it's to the left of the first non-zero digit. Zero in between, non-zero digits are significant. Trailing zeros are significant because there's a decimal place. So we have one, two, three, four, five significant figures. Okay? Now we have this. We have something 3 with one significant figure. Doesn't matter if I put a decimal, doesn't change it. Times 42.2222, right? That has 1, 2, 3, 4, 5, 6 significant figures. But our answer must have only one significant figure. So you plug this in your calculator. What do you get? You get 126.6666. But we have to round this off to one significant figure. And I think the answer is 100. If I put a decimal, is that the answer? No, because that would have three significant figures. So 100 has one significant figure, and this rounds off to that. I know it seems crazy, but that's what it is. All right, let's see. Let's go a little further with this. 3.0. Right? So 3.0 has two significant figures. So again, I have 126.6666. Now I need two significant figures. Is that 127? No, 127 is three significant figures. So this rounds off to 130. Again, no decimal. If I had a decimal place, that would be three significant figures. So 130 is two significant figures. 1, 3. The zero is not significant, and that's the answer there. So, all right, that's enough of that. You go review. All right, let's move on. Scientific notation, again, you know how to do this, but this is where you make silly mistakes, especially when you're pressured with no time and so forth. So remember, 10 to the A divided by 10 to the B is 10 to the A minus B. So we have 16 minus a negative 10 is 16 plus 10. This should be 10 to the plus 26. Okay, check me, make sure I'm doing everything correctly. Negative 4 minus a minus 20 is negative 4 plus 20. 20 minus 4 should be 10 to the 16, hopefully. And then finally, 10 to the 5th minus a minus 12 is 10 to the 5th plus 12 is 10 to the 17th. Okay, so that's pretty easy. All right, finally, let's see. How long does it take a ball to fall? 250 meters, 400 meters, 150 meters, 300 meters? Again, ignoring air resistance. We do not do the real world here, okay? All right, let's see. Our formula is T equals the square root of 2D over G. Remember what square root is? Square root of 25 is 5. Square root of 36 is 6. Square root of 49 is 7. Square root of 64 is 8, and so forth. Okay, we know how to take a square root here. We'll approximate. And once again, g, which is the acceleration due to gravity, which is 9.8 meters per second squared, we're just going to take to be 10. Okay, that's good enough for us. Good enough for us. Not good enough for Galileo, but good enough for us. All right, so d is 250. We have 2 times 250 is 500, divided by 10 is 50. Square root of 50 is very close to 7, right? 7 squared is 49. So the square root of 50 is 7.1 if you like, okay? 400, put D is 400, 2 times 400 is 800, divided by 10 is 80, square root of 80, well, 9 squared is 81, so it's very close to 9, it's about 8.9. This is real tough. 150, okay, what do we have? 2 times 150 is 300. 300 divided by 10 is 30. Square root of 30, 5 point something, right? Because 5 squared is 25. So easy, yeah? 300. 2 times 300 is 600. 600 divided by 10 is 60. Square root of 60, I don't know. 8 squared is 64. 7 squared is 49. 7.5, 7, I don't care. 7 point something, good enough for a multiple choice answer. Great. Ace. We're going to ace. All right. How high is a window if an object hits the ground after 2 seconds, 4 seconds, la 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 la? Well, here we're solving this for D. So D, if you remember, is 1/2 G T squared. Okay, once again, G is 10. So we got to be able to do this in our heads. All right, 2. So T is 2. What's 2 squared? 2 squared is 4. Good. Times 10 is 40. Divided by 2, 20. So after 2 seconds, the window, if it falls 2 seconds, the window's about 40 meters high. 4 seconds. So we take T as 4. 4 times 4 is 16. Times 10, 160. Divided by 2, 80 meters. 6 seconds. 6 squared, 36 times 10, 360. Divided by 2, 180. Okay. And then finally, 8 seconds. So T is 8. 8 squared is 64. Times 10 is 640. Divided by 2, 320. Geez, we're geniuses. If you take time to do all this on your calculator or you need to think too much, you're going to waste a lot of time and you're going to run out of time for the hard problems. So you should be able to do everything here very quickly. Okie dokie, an EM wave, okay? Well, every time you see EM wave, we have a couple things we should know. First of all, the energy of a wave is proportional to the frequency. The greater the frequency, the greater the energy. Remember the spectrum? We start out with, it's an inverse relation, right? C is a constant, the speed of light, F lambda. So it's an inverse relation, just like in Boyle's law. Okay, if you increase the frequency, you double the frequency, the wavelength halves and so forth. Same relationship. Okay, so it's an inverse relation. I'm telling you the period. The period is capital T. T is 1 over F, 1 over the frequency. So the frequency is 1 over T. So if I take 1 over, remember 0.5 is a half. 1 over T is 1 over 0.5 times 10 to the minus 8 seconds. Okay? So that's equal to 2 times 10 to the 8th. So the frequency is 2 times 10 to the 8th hertz. Fantastic. All right, so we know the frequency is 2 times 10 to the 8th. And therefore the wavelength, lambda, is C over F, is 3 times 10 to the 8th divided by 2 times 10 to the 8th. And what do we get? 10 to the 8th goes out. You get 1.5, and it's going to be meters. Because this is meters per second, and this is inverse seconds, right? Hertz is inverse seconds. So the 10 to the 8th power goes out. 3 divided by 2 is 1.5, so the wavelength is 1.5 meters. Wow. So everything to do with the spectrum has to do with the inverse relation. The speed is frequency times the wavelength. Remember the long wavelength, we start at radio, then we go to microwave, then we go to infrared or heat. Then we have that little gap of visible light, Roy G. Biv. So red has the longest wavelength, the lowest energy. Biv all the way up to violet. Violet has the greatest energy, the greatest frequency, the smallest wavelength. After the visible part of the spectrum, we have ultraviolet, right? White people's radiation. We like to kill cells. After ultraviolet, we get X-rays. And then finally, the most energetic, the energy, the electromagnetic radiation with the greatest energy is gamma. Okay, gamma. Great. All right, let's finish this off with a simple gas law. Constant temperature. Constant temperature, we know that's Boyle's law, right? So we know that PV, P1V1 equals P2V2. This is Boyle. So again, it's an inverse relation. So what am I doing? If the pressure is increasing, so the pressure is going from what? It's going from 20 atmospheres up to 80 atmospheres. Okay? So what's happening to the pressure? The pressure is increasing 4 times. 4 times bigger. So if the pressure goes up by 4 times, that means the volume has to go down by 4 times. Well, if the volume was initially 160 milliliters, we divide that by 4, the final answer is 40 mLs. Okay, so Boyle's law, inverse relation. Okay, let's see if we could squeeze in one more problem here. Suppose we have a gas, just going to shorten it, gas, with P is a constant. Okay, so whose law is that? Remember, Charles can't take the pressure. So this is Charles' law. Okay, and let's say initially, what do we have? Well, we have no P, we have V over T, right? So let's see, V1 equals, I don't care, 200 liters. T1 is equal to, let's see, I don't care, 327 degrees C. Okay. Now let's just say I make the new volume, suppose V2 equals 400 liters. So yeah, what is T2? Okay, so I'm doubling the volume. So Charles' law is V1 over T1 equals V2 over T2, but we have to have T in Kelvin. Right? We got to convert to Kelvin before we do our calculation. Well, I made this 327. How do we get to Kelvin? We add 273. So let's add 273 to that. Okay, we get 105. This should be 600. Okay, Kelvin. Okay, now I took the volume. So if I double the volume, I have to double the temperature, right? Charles' law, like the law of Gay-Lussac, is a direct relation. If you double the volume, you double the temperature. If you have the volume, you have the temperature. It's a direct relationship. So here, 200 liters to 400 liters, I've doubled it. Notice I cannot just double the temperature in degrees Celsius. That's wrong. You must convert to Kelvin, double it, so 600 Kelvin becomes 1200 Kelvin. And if we want the answer back in Celsius, you remember how to get back to Celsius? Well, to go from Celsius to Kelvin, you add 273. So to go from Kelvin back to Celsius, subtract 273. Okay, and what is that? I don't know, 927 degrees Celsius. That my answer? So that's our answer, if I subtracted correctly. Okay? So the gas laws, remember, are pretty straightforward. And all the gas laws, excuse me, all the gas laws P1V1 over T1 equals P2V2 over T2. This is all the gas laws combined. Okay, so if I ask you, what happens if I double the pressure and volume? What happens to the temperature? The temperature would also have to double, right? Because if I made that a 2 and a 2, then this has to be 4, so the ratio stays the same. Okay? So all the gas laws are here. If If T is a constant, if T1 equals T2, we said that's Boyle's law, Boyle on your butt. We get rid of T, we have P1 V1 is P2 V2. Boyle's law is inverse relation. If the pressures are the same, P1 equals P2, we get rid of pressure. V over T is V over T. We said constant pressure is Charles' law because he can't take the pressure. Again, that's a V over T. It's a direct relationship. So if one increases by a certain amount, the denominator increases by the same amount. And if the numerator decreases by a certain amount, the temperature decreases by the same amount. But you must do all your calculations for temperature in Kelvin, so you have to convert. Finally, the law of Gay-Lussac is constant volume, so we take V out. We have P1 over T1 is P2 over T2, same exact structure as Charles' law. Okay, it's a direct relation, and all calculations must be done in Kelvin. Okay, so thermodynamics, we'll do a little more with that in the next lectures. All right, we'll just keep going and see how it goes. All right, be well. See you next time. Peace.